All right, 11.2, we started last time talking about vectors in space. All we had looked at thus far, and we will do a couple more things with it, are what points in space, what sort of images in space look like. So we had talked about this particular drawing of plotting a point in space, and we had talked about what the distance looked like between points, and it's sort of just this extended view of the distance from really what we've seen before. And then we had talked about looking at whether or not a triangle was isosceles or right or possibly both or neither. And we had done that by looking at the lengths of the sides. We noticed that it was isosceles because there's two of them that were the same. And the way that we confirmed that it wasn't a right triangle, because we didn't do it formally. We did it informally, right? We said there's no way that can work because the third side that was not equal, right, was actually smaller. And if it was the non-equal side, it would have to have been bigger, right, if it was the side of a hypotenuse of a right triangle. So we knew it wasn't a right triangle. All right, so we're going to take a look at a few more couple more extension things before we get into looking at vectors. So midpoint. So midpoint is done, much like distance formula, with just this one extra caveat that we have the z-coordinate on the end. And so when we find midpoint, we're averaging things, right? This is just an average. So we average the two values together and divide by 2. So for the first one, we would have 3 plus 1 divided by 2. The second one would be 4 plus 8 divided by 2. And the third coordinate, the z-coordinate, would be 6 plus 0 divided by 2. Does that make sense?
Why is it divided by 2 again?
It's an average.
Okay.
So finding a midpoint averages the two values together and finds something halfway between. So we have that factor of 1/2 or division by 2. So the first one ends up being 4. And then what do we have? I'm sorry, 4 over 2, so 2. Sorry, getting ahead of myself. Then in the next one, we would have 4 plus 8 over 2, which would be 6. Yep. And then 3. So 2, 6, 3. Okay, is that okay? It's kind of as expected. It's not anything really different. Now this one's a little different because we haven't talked about spheres in a while. We haven't talked about circles in a while, but the equation for a circle looks something like this. Let me write that one down first, and so that you can see the extension. X minus h squared plus y minus k squared equals r squared. Does that look familiar? You've seen it before. It's also the distance formula. Check it out. Do you see the distance formula there? And it's also the Pythagorean theorem, right? A squared plus b squared equals c squared. Okay, all those things are the same thing. They're measuring distances in the same way. So if we're going to do a sphere, what do you suppose is going to happen? There should be an extra term, exactly. So I'm going to have my x minus h squared, my y minus k squared, and I'm going to have a z minus... Somebody pick another letter for me. I don't even think I have a letter written down for myself. All right. Nobody, huh? B, thank you. Z minus b squared. There's probably a standard one that's in your book, but I don't remember what it is. So r squared. And then we're going to take each of the components that they gave us and plug them in. So our center point for our center's x value is 3, so it's x minus 3 squared. For the y value, it's y minus 1 squared. The z value is 4, so it's z minus 4 squared, and then r is 2. 2 squared is 4. Straightforward enough? Okay, so three-dimensionalizing our circle into a sphere. And then we're going to remind you the way we handle things when we're taking kind of a messy expression of a sphere. In this case, a sphere. We've done it with circles before, and we're putting it back into standard form. So here is a sphere, but it is not in the form that we just saw, and we want to put it back into that form. And so you had a process called completing the square. Do you remember that? Oh yeah, or it's coming back around again. It just keeps coming back. So the way that worked is that you take a look at what your x values are, okay, kind of group them together. The y values, there's only one, and then the z values you're grouping together. Okay? So I'm going to write this out with a space after it. So I'm separating this apart. I have my y squared. Y squared Doesn't really need a space after it because it does not have a linear term, so I'm not going to put one in there. And then I have my z squared minus 4z, and I'm going to leave a space after it. And for the moment, it equals 0, but not for long. So if you'll remember, the key to completing the square is this number that we add into each of the locations that I've underlined in yellow, which is b minus 2 squared. Sorry, b over 2, squared. Okay, so what is b? Well, b is the linear term's coefficient. In our case, we have a -2 and a -4. So they're very friendly terms. Okay, so the way that I get this missing spot right here to complete the square, thus making this a perfect square, is to take this value, -2, divided by 2, and square it. What does that give me? 1. And in the blank, I put a +1. But I can't go just adding 1 to the equation. I have to balance that by adding 1 to the opposite side as well, right? This is a scale. We've added 1 over here. Now I have to add 1 over here to bring the balance back to it. So we're going to add 1 over here to balance it. Now we're going to do the same thing with the 4. All right, so I'm going to divide -4 divided by 2 squared. What do I get? It's a 4. So there's a +4 here, and I have a +4 over here to balance it. Is it possible that you could end up with something that's fractional? Well, yes, right? If this were an odd number and you divide it by 2 and you squared it, you're going to get something that's going to have a fraction involved. Okay, put it in, move it to the other side. You and your calculator, between the two of you, can handle fractions just fine. Okay? So is it nice and pretty? Not always. This one is, but it's not always. So here's why we do this, though. So as a reminder, the reason we do this is because this factors very nicely. It will factor into a component that looks like this at the front. X plus or minus something and then squared. That's the reason we did this. So I'll write out the first one to show you that it does this, but then I'm not going to write it out ever again. This factors as x and x. The subtraction in the middle makes these negatives. The one at the end says there's a 1 and a 1. If you multiply them back together, you do in fact see that this is x squared minus 2x plus 1. So generally speaking, we jump down to this step where it looks like this. So when I look at this expression and I write it in this form, here's the way I think about it. I think about dropping this x down. I know it's going to be squared, and it's simply the middle term divided by 2 that goes here. That's what goes at the end, the middle term divided by 2. Okay? The next component was y. Now, the y doesn't have anything grouped with it. If you want to write it like this, just to remind yourself, you certainly can. It has a 0 component for its part of the center. If you want to not write it, that's fine too. And then over here, again, we know we're going to get a z and something squared. So I take my middle term, the b term, that linear term, -4, divided by 2. That gives me -2. It means I have a -2 here. Okay? And then what do I have on the right-hand side? 5. And I'm asked not only to find the standard equation, which I did, but then to identify the center and the radius. So what's the center of this sphere? It's going to be an ordered triple, right? Like over here, they gave me the center of the sphere, 3, 1, 4. What's the center of our sphere? 1, 0, 2. And you'll remember, because you did it, but just as a reminder, right, it's the opposite sign of what's inside. So if the sign inside had been positive, then its value down here when I identify the center would be negative. Make sense? What's the radius? Yep, the radius is square root of 5. Okay, you ready to get some vectors now? So this is all just like preliminary, like three-dimensional geometry stuff is what we really just did right there. The title of the course really actually says Analytical Geometry in Calculus 3. So we do end up with some of that in here too. But we are moving on into the vectors now. So the vectors here are going to look again and feel much like we did in section 11.1, but just with this extra component because there's 3 components on the end. We're going to find the vector and its magnitude. So it gives us an initial point and a terminal point. Do you remember what we did with an initial point and a terminal point to find the vector? We subtracted them. Which direction did we subtract?
The terminal point minus the initial.
Right. Do everybody remember that? Terminal minus initial. So if I want to find my vector, And I'll use the notation we've done like this. If you want to use IJKs, you can do that too. So terminal minus initial, somebody tell me what I'm going to get. Thank you, Sophia. 1, -1, 6. Everybody good with that? Okay, how do I find magnitude? What does that mean first? What is magnitude? It means length, right? Magnitude means length. Okay, how do I find the length of a three-dimensional vector 1, -1, 6? Again, it's going to look like the distance formula. It's going to look like my equation for my sphere, right? It's going to look like all these things with just that extra component on, like we added to those other components, those other features. So I'm going to end up having 1 squared plus, right? Signs don't matter, so that -1 in the middle is also a 1 squared, and then 6 squared. So what does that give me as a value? 38. Yep. And screw it, 38 doesn't simplify. It doesn't break down into anything nice to simplify it out. If you were asked to round this to decimals, you certainly could do that. For the most part, we keep things exact, but they could ask you to do something, especially in an application type problem where they did. So. Okay. Using our vector, I've turned too many pages. Using our vector above, okay, the one we just found, we're going to find 2 times the vector, a negative times the vector, and 2/3 times my vector. And I will write my vector at the top. I'll call it V since you're calling that here as well. It was 1, -1, 6, right? Okay, so what would I get if I'm going to do 2V? 2, -2, and 12. What would negative V be? -1, 1, -6. What about 2/3 V? And then what? Something else. Is it 4? Sorry, I have a typo written on my paper wrong. I don't know what that is. I'll have to fix that later. Okay, 4. Thanks. All right, all good? Okay, so it's just like 2 dimensions, right? It doesn't change at all, just have an extra component. All right, here's one that's given in the IJK form. We have a U vector, a V vector, and a W vector, and it wants us to find a composition vector that is U minus 2V plus 3W, right? We did this in 2 dimensions. We're going to do it in 3 dimensions. So any of those constant multipliers, just like over here, are going to multiply the vector by a value. Addition and subtraction is going to operate just like you would expect. We're going to add things together. We're going to subtract them just like they were real numbers. And we're going to work through those details. So we have, and I'll write it out a little bit detailed, maybe more than you need here, but if you need it that way, you see it. So we need vector U, so that's a 1 component. Actually, you know what? It's an IJK. Let's just keep it an IJK for this one. So I have the I is 1, 1I. And then for V, it's I as well, but it's supposed to be minus 2I, because that's what the V says. And then on W, it's already a 2I, and it's multiplied by 3, so it's plus 6I. Okay, that would be all the I components. Okay, so I'm multiplying this one by 3, and this one by -2. Now we're going to do the V component, Now we're going to do the J component with this one. So I have a -4J from U. I have a -3J times a -2, so that's a positive 6J from V. And then I'm going to have plus 3J from W. The last one is going to be -2K from U. I've got -2 times 4, so 8K from V. And then minus 3K from W. And all of these I's and J's and K's should have hats on them. I think I got them all on. All right, so what is my result for I? 5i. Oops. What about for j? It's also j, 5, yeah. 5j. And for k? -13k. And you don't have to do it in this form. I just haven't done very much in this form, so I thought I'd throw one in there. That's why I was getting a little messed up, is because my notes don't have that in there. But we did it just fine. Y'all did great. All right, how about the magnitude then? What's the magnitude of z, the z we just found above? Well, remember, notation for magnitude is like this. I didn't write the notation down the last time, so we'll write it down this time. So last time we did a square root. And then we're going to square each of those components, right? So I have 5 squared, 5 squared, and 13 squared. So 25, 25, and is it 169? Is that right? Okay. So what does that give me? 219? Okay. Does 219 simplify? I don't have anything written down. I don't think so. Dylan's checking for us. You don't see anything, do you? Yeah, I don't think so. I think 219 is, if not prime, at least it doesn't simplify. So, okay. So this is our vector. Whoops. Our vector z is not negative, sorry, 5i plus 5j minus 13k, and we said that its magnitude, no, that was right, is square root 219. So now it wants us to find a unit vector in the direction of z. Do you remember what we did with unit vectors last time? How do you do that?
Divide the vector by the magnitude.
Yeah, you divide each component of the vector, which is in essence exactly like Adrian said, dividing the whole vector, right? Each component by the magnitude. So we would have our unit vector divided by the magnitude of the unit vector. And so that would give us 5 over the square root 219. We'll rationalize in a minute. I plus 5 over the square root of 219. J. And minus 13 over the square root of 219. Okay. And then what do I get when I rationalize that? Five square root 219, right? Over 219i plus 5 square root 219 over 219 j minus 13 square root 219 over 219 k. What do you suppose the opposite direction of z is going to mean? What's it going to do?
Change the signs.
Yeah, so we change all the signs, right? We're just going to change all the signs. So everything remains the same that we just did. So I'm going to copy paste and I'm going to adjust my signs. So we have a negative on the first one. We have a negative on the second one. And then we have a positive on the third. I don't know where that stray mark's coming from. I probably moved something I shouldn't have, but. Is that right? Does this feel any different than it does in 2 dimensions? It shouldn't. It's all the same stuff. We're just doing it with a third piece to it. Now this one's a little bit different because we're talking about some parallel vectors. We haven't talked about parallel vectors before. Parallel vectors are 2 non-zero vectors. When there is a scalar c such that u is equal to c times v. I don't know what that 9 thing is at the end. Looks like a typo I've got from something hanging over, so scribble that out. U and V are parallel when there is a scalar multiple such that one is a multiple of the other one. Now, that seems interesting because one of the things that we encountered back in section 1 is that if we take a vector and we shift it back to the origin, we sort of recenter it, right? We say that those are exactly the same vector, correct? So if C is equal to 1, which it doesn't exclude, then that means a vector is parallel to itself, correct? Because that's what it means to be shifted around. So a vector that's parallel means that it, for the most part, means it's exactly the same, or it's just a scalar multiple. It's longer or shorter than it was before, because we have the ability to recenter it and call it the same vector as we had before. All right? So we're taking a look to see which of these vectors is or are parallel to Z. So Z is 3, 2, negative 5. And what we want to see is if there's a scalar multiple that will achieve each of these vectors. So taking a look at the first one, what do you think? Is there a number that I can multiply it by and get the first vector on the A? Yes. So this one is a yes, and the scalar multiple is a negative 2. If I multiplied every component from Z by negative 2, I will get the vector listed in part A. How about B? Yes. Do you know what it is, Jackson?
2/3.
The C value is 2/3. Now, if you're looking at this and you're not readily seeing how we're getting the numbers, just take one component. We'll go back to A because it's easier to see, but 3 times what is equal to negative 6? Oh, it's negative 2. So negative 2 is what I'm going to go with, and you're going to check and see if the other two work for negative 2. If they do, then negative 2 works for all of them, and it's a scalar multiple, and we got it, right? And if it doesn't, then the answer is just going to be no. So how about letter C, That one's not going to work for exactly the reason that I just mentioned. So it's still negative 2 if I try to go from X component to X component. But if I use the Y component, right, the J component, I should say, the J component 2 times negative 2 would be negative 4, and this says positive 4. Another way that you can very quickly identify that it's not going to work is that the original vectors, first 2 components are positive, they match, in other words, and they aren't on this one. Right? The signs would have to actually correspond, and they simply don't. And so down here, you can see that readily as well, correct? I need to have my first 2 components, the I component and the J component, both be the same sign. They could be positive, they could be negative, but they need to match. And the third one needs to be the opposite, because that's what's happening in vector Z. So this one also will not work. There's no they are not parallel vectors. Okay, have you seen or heard of collinear points before? Yeah? Okay, so collinear points are points which lie on the same line. They can be determined by finding if the points form parallel vectors. Okay, so we're going to use vectors to decide if we've got collinear points. So we have the points 4, negative 2, 7, negative 2, 0, 3, and 7, negative 3, 9. And we're going to decide if they are collinear by establishing the vectors that are created from these points. Just so that we have a common reference point, let's call them A, B, and C as points. And we will find our vectors AB and AC. You could do BC if you wanted, it doesn't matter. Just pick 2 and then pick 2 of the different ones and you form 2 vectors. All right, so what is the vector form? I'll use vector notation this time. What is the vector formed for vector AB? I'll start out. Negative 6. What's next? 2. Remember, you're subtracting terminal point, which we've identified the way we listed it as B, minus the initial point. And what's the last one? Negative 4. Good. And then I chose A and C. If you choose B and C, that's fine. You'll get the same. You won't get the same vector, but you'll get the same answer to the question of yes, they're collinear or no, they're not. Those things will match up when we're done. So if I do AC, what am I going to get? 3, negative 1, and 2. Okay, so we found 2 vectors. Okay, they aren't the only two vectors we could have found. There's a third one we could find if you wanted. And we want to see if one of them is a scalar multiple of the other one, right? Is there a scalar multiple? In other words, are they parallel? Are these parallel vectors? Yes. What's the C value that you got? Let's say we're going from AB down to AC. Negative 1/2. And you could go from the other direction if you wish and call it -2. That'd be fine. So it's either negative 1/2 or -2, depending on which one you're moving from as your initial, and the other one is the other one. And so this means, so the points, I'm off the screen, hang on, are collinear.
And collinear is parallel.
Collinear means they lie in a single line, right? So if you did it in 2 dimensions, we can draw it the easiest, right? They look like this, right? They all lie on the same line. You can do it in 3 dimensions, of course, as well. The same description holds. They just lie in the same line. So if you can imagine what we really just did here in a 2-dimensional, because this is a 3-dimensional, I get that, but in a 2-dimensional sense, is we found this vector. And then, because I did it in a different color, let's try it with yellow. And we found this vector.
Okay.
And we said they're scalar multiples of each other. And you can imagine that this wouldn't work if we were doing things that weren't collinear. Like, let's say that this point right here, we're over here, and I found this vector, right? That would be AC, and I found the vector AB. They will not be collinear. I mean, they aren't collinear, but they will not actually be scalar multiples of each other when you look for the multiplication factors. So, okay, I think we have one left to do. We're going to use vectors to show that the points form the vertices of a parallelogram. Okay, y'all remember what a parallelogram looks like? Okay. Some of you are drawing it in the air. I don't have an actual tool for parallelogram, but we'll see what we can do. So in 2 dimensions, it would look something like that. Close? Yeah? So what does it take for something to be a parallelogram? What are the descriptors that you could use?
Sides.
What's that?
2 sets of equal sides.
2 sets of equal sides. Anything else? The opposite angles end up being congruent, right? That's true as well. Nobody's used the word parallel, though, yet. The sides have to be parallel, right? Okay, actually, the definition itself says that it's 2 pairs of parallel sides.
Oh.
All the other things come about as a result of that. But they are true. They are true. So we're actually trying to decide, because this is supposed to be a parallelogram, or it says to show it. So we know it's going to work, correct? It said show, not, yeah, okay, so it says show. So we're going to have to figure out which of these go in what order. So, right, like imagine this is a 2-dimensional picture, but imagine that this is ABCD. And I didn't know that it went ABCD, and what if instead I was supposed to go ACDB? Right, that orange shape, because I messed up the ordering of the letters, wouldn't have been a parallelogram, right? But a parallelogram does exist. So we need to be a little bit careful and a little bit aware that just because something doesn't work the order we pick doesn't necessarily mean it doesn't work. We could have picked a different order, and we need to be aware of that as we work. So we're going to try and label some of these points. And I think I labeled mine just in order like I did last time, so we'll do that again, A, B, C, and D. And we're going to find the vectors. So I would like for you to take a minute. You do not need me to find vectors for you. You know how to find vectors now. So I would like for you to find these vectors. We're going to start with these. I've written down AB, BC, CD, just going from one to the next, and DA. Okay, let's find these vectors and see what happens. So find those 4 vectors, and then I'd like for you to compare notes with somebody else, make sure you have the same vectors, and we'll compare it with mine as well. So some of you have stopped writing. If that's you, grab somebody nearby and just make sure that yours match. Okay, Connor, what'd you get for AB?
1, 2, 3.
Excellent. Does everybody get 1, 2, 3? Great. Preston, what'd you get for BC?
What?
It's okay. Just the next one in the list. BC, do you have that one? Or did you do a different order of things?
3, 1, 2.
Okay, I have -3, -1, and -2.
That sounds right.
Does that sound right? Does everybody have negatives? Or I could have it written down wrong. Okay, thank you. All right, Peter, what do you have for CD?
1, 2, 3.
Excellent. And Lauren, what do you have for DA? Okay, do you see any of these parallel to any others? Oh. Oh. I do. I have mine opposite as well. The answer is it doesn't actually matter because we're just looking for them to be parallel, so it wouldn't make any difference if we did the orders backwards. But if we're looking at the terminal points the way I've written them, this is what I have. Is that what you guys are asking? Okay, cool. All right, do you see anything that's parallel?
1, 2.
The 1, 2, 3s, right? These two are parallel. Okay. Now, if this is a parallelogram, I need 2 pair of parallel sides. I've got 1 pair. Are the other 2 sides that I've listed here parallel? They're not, right? These 2 are not parallel. Okay, but it might be that it's like my orange picture, right? Maybe I went in the wrong order. Do you know what I'm saying? Right? Like when I did the orange versus the white of the original shape, they shared 2 of the sides, right? A, B, and CD are the same, but the others are not the same sides. There are 2 other sides we can check, though, to see if this actually still ends up being a parallelogram. The sides that we're missing are BD and AC. Okay, can you see those in my picture? B and D could form a side. It's my orange in the middle. And then A and C could form a side. Right? That's another option of how I could have lettered my points or organized my points. So find B, D, and AC. Do you have one, Adam?
Yeah.
What do you have for BD?
BD is -2, 1, 1.
Okay, good. How about you, Austin? Do you have the second one?
Yeah, -2, 1, 1.
Okay. So what does that tell you? These are parallel as well, right? Okay. I need to not use black as a backdrop because it runs into the actual on the screen backdrop and I can't tell the difference on my screen. All right, parallel. So I do have a parallelogram, but it wasn't the first ordering of things I picked. So what would it look like to have this parallelogram? Well, for my parallelogram, A, B, D, C forms a parallelogram. Right? AB right here and CD are the 2 sides that go together, right? And then I need BD and AC to be the other 2. So the ordering of it, I initially had listed ABCD as it was. Didn't work, but another ordering did. So yes, we do have a parallelogram, but this one is a parallelogram. Notice ABCD is not. That's like my orange above. if I unlabeled the letters, and this one is like the white one that I did above. So I don't think I wrote it in there in the right way for that to be true. A, B, yeah. So if I switch these letters, you can actually see it matching up with the images that I created then. I didn't write the D in there. I meant to write C down there. I apologize. Yeah, that's the one I want. Okay.